All right. I think we can start now. Hello, everyone, and thanks for joining my session regarding the RAG components. My name is Vincenzo Gambino. I've been working with Drupal for 16 years now. I'm also an author. I wrote a book about Jamstack development, where I built application using Gatsby and Sanity, Gatsby and Drupal, and also Alexa and Sanity. I'm also a speaker. This is the way I like to contribute back to the Drupal community. And I'm also the co-organizer of the meetup group in my own town, Palermo, of the group Drupal-aware. And I'm also the co-organizer of the Drupal Camp Italy, which took place last year in Rome. And this year, we'll be back in Bologna on the 22nd of October. The call for paper and call for sponsors are open. And if you like Drupal, tortellini, lasagna, and spaghetti bolognese, that's the right event for you. So today, we're going to talk about RAG, the fundamentals of RAG. So all the components, and we're going to see the difference between the semantic search and the keyword search, how we can combine them in the hybrid search, and refining the result from both the searches. Then we're going to see how we can improve the prompt, how we can evaluate our system, and also we're going to see how an agentic run can work, and then there will be some final tips and thought at the end. So first of all, we need to think about the problem that we have at the moment. So the LLM are amazing, we know them, but they are frozen in time. So they are training on public data. They don't have access to your content, so they have no knowledge of your Drupal site. And they can always have generic answer to specific question. The RAG system creates a bridge between the LLM and your content. So what it does a search and answer. So it goes into your system, so you provide the content of your system, and can answer question based on your content. So it's good for, so this is the base, sorry, of RAG. So the users ask a question. We do a database search. We pass the result that we got back from the database alongside with the question. We pass it to the LLM, and the LLM will generate an answer from this question based on the context that we give, so the content from our site. So it's useful in many places. So the search and Q&A. If your company has internal knowledge that you want to add, and want to use the LLM to produce documents or other things, recommendation for e-commerces, for example. And then if you have a customer support chatbot and you want to kind of train the LLM or give the information about your product to the LLM, then you can have domain-specific support. Why this is useful in Drupal? Because, well, Drupal is amazing, we know. It can handle a really large volumes of structured content, all combined with them and related with taxonomy, relationship, and references. You can update your content that will be always available to the LLM, and you can build a search that needs context and not just keywords. It can be a chatbot or even a simple search that can understand what the user is asking. So let's dive into the numbers and algorithms of RAG. So the first number that we see is tokens. Tokens is the numeric representation of a word. So because the LLM do not understand English or Greek or Italian, they do understand numbers. So we take those words, we divide it into tokens, and then we convert it into numbers. Bear in mind that those numbers are not the meaning of the word, it's just the representation of the word in numeric. For the meaning, for the semantic meaning of the word, we use embeddings, which is a vector, is a coordinate that gets stored in the vector database. And when you compare two vectors, if they are close, the terms are related. If they are far away, the terms are not related. So this is an example. So we have the word Drupal, CMS, taxonomy, and module, and then the word banana. We can see that the coordinate of the first four words are really close to each other because they are related, while the word banana is far away. And in a vector database is represented in this way. So we have here a cluster of terms related to Drupal, taxonomy, module, and CMS. And then far away, we have the the word banana. So this is a vector database with all the coordinates, so the embeddings, and the terms get stored in these dimensions. So now when we perform a search in a standard database like MySQL, we know that there are columns and rows, so it's easy to search. But how does it work in a vector database where we have spaces, dimensions, and distances? Well, we use the algorithms. So first, we have the KNN and the ANN algorithms. KNN is the k-nearest neighbor, which is really, really precise, but is slow. And then we have the variation, which is the approximate nearest neighbor, which is really fast, but a little bit less accurate than the KNN, but still acceptable and is widely used. So the KNN algorithms, what it does, it compares all the vectors against the query. Because when the user asks a question, the question gets embedded, so it has its own vectors, and then compares those vectors with one that are in the vector database. And so what it does, the KNN, it compares all the embeddings from the query with the vector that has in the database. So it means that you have 1 million vectors in your database. It needs to load all those and compare it one by one. So it's really slow, and when you are scaling, we have more data, of course, it becomes slower and slower. Then we have the ANN, which is the approximate nearest neighbor, and we have the variation. So one of the family, the algorithm from the ANN is the navigable small word. What it does not load all the vectors. It does not compare all of them. What it does is start searching the closer one by one to the query with the document that we have. So it chooses an entry point in the vector database, a random one, and then it compares the one close to this point. So it says, so the query is here. So I say, this one is closer than this one and this one. So I jump into this one. Then it compares the distance with this one and this one and this one. So I say, this is closer. So it jumps on this one, and then so on until it comes closer to the query. This is a really good algorithm. It's used. But there is another variation which improves this one, which is the hierarchical navigatable small word. So what it does, instead of having just one dimension, it creates different layers. And from this layer, it starts searching in the same way. So what it does, it starts from layer 2. So you have a random entry point, and it checks all the vectors around. So this is closer. So it finds it, and then it goes to the other layer, and it loads more vectors around, and then again jumps on the closer until it finds the layer with where the vector is acceptable, is at an acceptable distance to the query, and then returns the result. But the other question is, how do they calculate the distance of those vectors? So it's not just number comparison, but it's a proper similarity matrix that we will see here. So this, you can find it also in the Drupal modules, in the Search AI module. You can choose one of those. So you can use the cosine similarity that measures the direction of the vectors. So if two vectors are pointing in the same direction, they are really related. If they start to go in different direction, then a little bit less related. So in our case here, we measure the angle, and then we do the cosine of the angle 20 degrees, and we get the number here. Then we have the Euclidean that is measuring the distance between the two vectors. And then we have the dot product, which basically one vector casts a shadow on the other vectors, and then measures this shadow here. The longer it is, the more related they are. Otherwise, it's the other way around. And the same thing here. So less the distance is more related. The same thing here. So this is the workflow of RAG. So we have the user asking a question. The question gets embedded. We return the top k results. We can decide how many results we want to return from the vector database. We define with top k. Usually it's around 10 is acceptable, or 5. So we return the result defined here. We pass it here to the LLM alongside with the question. And the user, then the LLM will generate an answer based on this. So now, here there is another thing that I want to talk about, because if we can pass some context, why can't we just pass all our content in the context instead of having a vector database? Well, that is possible and is called CAG, which is Cached Augmented Generation, where we put the whole site knowledge, the site content, into the context window. Because modern LLM have really, really large context windows. I remember a few years ago when we started with ChatGPT, we had like 2,000 tokens context window, 4,000 and 16,000 was amazing. Now we are in the average of 200,000 tokens or 1 million tokens as well. And then it's a simple approach because there is no retrieval layer, there is no vector database. So it works well with small and focused knowledge bases. You have always fresh content. As I said, it's simple architecture, and there is no retrieval, but it's good for only a good limited documentation set, because you pay per token when you do a request. So every time you pass the whole content, the whole context to the LLM, you pay those tokens. Even if it's cached, you can cache it, but you're still paying for them. Then, if you have a Drupal site and you add more content, then of course, if you have 1,000 nodes with 2,000 tokens each, you have 2 million tokens, 200 million tokens, so you cannot pass that to the context windows. Then it becomes lower. When the LLM have a really, really large context window, it starts focusing on the wrong part of the document, so you can get a wrong answer or not accurate answer, and it's not practical for Drupal. Even though Anthropic say that you can pass up to 200,000, 500,000 tokens in the context windows, I still tend to pass less and not use cached when there are like lots of tokens. So how can we solve this problem? We can solve this problem by using RAG, and when we store the data in our vector database, we chunk them. So we divide it into small pieces. And then we can also add the metadata. But let's start with the chunks. So what gets stored actually in the vector database? We have the text, so the original content that we want to store, the embedding vectors, so the coordinates, the numbers that they have, and then the metadata. So we can add ID, non-ID, taxonomy, timestamps, and many other parts. And all these three components, they work together when we do a search. This is how it looks like. So we have the chunk ID, the vector here, the text, and then the metadata. This, if you have any system like, for example, Pinecone, you can see those as well. You're able to see them. So chunking is the technique of breaking down the content into smaller pieces, because each piece then becomes a searchable unit, and each chunk gets its own embedding, so it has more accurate checks. And then when we do a search, we retrieve just the chunk that we need and not the entire document. We can load the entire document later if we need, but for the moment we get just the part that is important for us. So this is an example of chunking. So we have the Drupal 10 migration guide node, and the body has 500,000 words. So we divide it into chunks. So we can do the first part, which is introduction prerequisite, preparing your module, database migration steps, testing, validation, then post-migration cleanup. In this way, instead of storing the whole document, we divide it into chunks and we store them. And if we do a search, we just search for the chunk that we need and we retrieve just that part. Because if you want to ask, for example, how to prepare the database migration step, we don't need to add in the context this part here and the other part. We need just this part here. Then we can add a reference to the content. If the user wants, can go and see the full content. So the benefit is the smaller context. Context means lower API costs. You can have a better attribution, and you can search more chunk instantly. And then when you update the content, of course, you can just do the embeddings of the chunk and not of the entire documents, which is going to save some money as well. So these are some of the techniques that we use for chunking. So we have the fixed size, and that we split the content every number of token. Recursive, where you can define, I don't know, an HTML tag on some other delimiter to break down into chunks. The semantics, when we pass it to the LLM to understand the meaning and create the chunks. Or, because we are in Drupal world, we have the Drupal specific. So we can do by field, paragraph type, entity, and so on. So the fixed size chunk, as we said, split the content every number of tokens. So for example, an article with 300,000 tokens, we can create 6 chunks, 500 tokens each. But the problem is that the chunk ignores the boundaries. So for the pros and cons, we have, it's simple to implement the fixed size. We can predict the chunk size, of course, and it works with any content. The cons are that it breaks the semantic boundaries, so it breaks the idea mid-thought, for example, and it has a poor context preservation. But there is a workaround for that. For example, you can add an overlap. So for example, in your content, you create the first chunk of 500 tokens. Then in the second chunk, you add 100 tokens from the previous chunk, so it has a little bit more context. The one that really works better is, of course, is semantic chunking that split the content alongside with the natural boundaries. So what it does, it will read the content, will understand it, will understand all the section, even looking at the HTML tags, and then it will divide it into chunks, and then it will pass it to the vector database. The Drupal one, the pros and cons is that the semantic chunking preserves the semantic coherence. They completely stay together and is even better for retrieval. The cons is that the LLM has to go through the content, divide it. We don't have ownership on how many chunks it creates. So we have like a little bit of unknown how many chunks it's going to create. And then depends on how well your content is structured. Then we have the Drupal-specific chunking, where we use the Drupal natural boundaries, like field, content type, paragraph, and any other entities, to create those chunks. And the pros is that we use the existing structure, so we can keep the natural semantic boundaries, and then we can use the metadata from those information as well. The cons are, again, that is only Drupal specific, so we cannot port it into other systems. If you have different content source, it will not work. It requires you to understanding your content architecture and how you want to chunk it. And then again, we have a variable chunk size. But again, the good part is that we can add the metadata, because metadata are really important. So they are structured data about your content. They are not vector, they're not number, they are just words that you can actually add a JSON object to the embeddings. So you can use it then for filtering and attribution, personalization, and then this complete the semantic search. How it looks like. So what you can use, for the metadata. We can use the content type, the status, language, the ID, whatever information we want to add to the embeddings. We can also add taxonomy relationship, anything we want, any information we want to use it as a filter, we can add it to the metadata. Even like the field type, so if you want to filter just by body summary or some other field or by entity type. And then when it gets stored, it will get stored like that. So we have again the ID, the vectors, the text, and then the metadata with the node ID, language, and any other information that we want to add. So it improves the retrieve it by filtering, as we said. So we can do the pre-filter, so we can filter before we do the query. So we can add that to our query. Post-filtering, so after we get the result, we can filter it, and then again we can do by ID or body field or any other information that we want to add. And then these are the type of filters that we can use. So it's exact match, multiple values, range filter, and existence check. Okay, so any questions so far? Yes?
Prior to the vectorization of the data, do you apply some subword list to filter out fill words or something? Or you just throw in all?
No, you can. It's something that you need to prepare from your Drupal site. So when you want to start do the chunking, you decide which field you want to pass, and if you want to ignore some content or some stuff like that. Okay. Any other question? Okay. So now we'll talk about hybrid search. In this talk, we will talk about the keyword search, now in the next slide, and we talk about the semantic search. So the difference is that the keyword search, we're going to see the sparse vectors, and the semantic search, which is also called dense vector, have some differences. So the keyword search matches the exact word, while the semantic matches the meaning. The sparse vector uses the algorithms like BM25, TF-IDF, while the semantic, as we saw, is using the vector embeddings. When we search with the keyword search, it's actually matching the exact word. So migration only finds document with migration, while in the semantic search, if we search for migration, you can also find upgrade, transition, and moving. So, but they can work together. So let's see how the sparse vector works compared to the dense. The dense, as we know, are coordinates going into the vector database, while the sparse are basically document index, where we have the list of our documents here, and then here the list of all the words that are contained in our document. All the value here that starts with 0, and then if the word is contained in the document, it gets 1, and so on. So every time if it's in the document, it gets 1. Otherwise, is 0. And it does it for all documents with all the words. When we perform the search, what we do, compare it to the semantic search, so we break it down, the whole query, into single keywords, and then we compare it with the document metrics that we created before. So every time that a word is contained in one of the documents, it gets 1 point, and then at the end we have the score. So at the end of the search, so after it counts all the keywords in the document, we have something like that. So we have here the score, and the document with the higher score will get selected. But here, as we saw, we have a problem. So this content, based on this query, has 50 points, but is not related to the query that we have done, because everything that happens, it was because A has 32 points, was mentioned 32 times, so it got higher in the ranking. So how do we fix that? We fix the issue with the common words, like a, and, to, and, or what, for example. Pardon?
That's a software list.
Yes, exactly. Or we exclude when we store it, or we use the algorithm, like the term frequency. So what we do, we basically take the number of keywords that are in the document, and we divide it by the document length. So in this case, we know if it's common or not. So the less common will have higher points than the most common, like A or 2. And then what else we can do? We can do the inverse document frequency, where we compare the terms, how it's doing overall across all the documents. So we weight the term using the ITF. So what we do, we term in the document, multiply the log of the total document that we have, divided by the document that contains those terms. In this case, we can have nice results. So at the end, we'll have something like that. So where the document frequency here is the word controller is in 5 documents out of 100 documents, so I get this score, while the word 2 is in 100 documents, out of 100 documents, it gets score 1, so it's higher. So we invert it, so we do 100 divided by 5, which is 20, and here in this case gets again 1, but 20 is too high as a number, so we score quite a lot, even if it's a really important keyword. So we do the log of this of the score here, and we get 130. So we normalize the result, while the log of 1 is 0, so we will get 0 points. So most common word will get really low point. So at the end, we'll have something like that, where the word controller gets 0.9 here and here. The word create as well gets 0.9. And while the word like how, to, and create, it gets like a 0.1. So at the end, with the score, we have 2.5 for document 1, which contains create, Drupal, and controller. So it will be really related to the query. And then document 4 is 1.7, even if it hasn't got create, but has Drupal and controller, so it's talking about the controller. while document 2 and 3 that haven't got the word controller or create, they get a low point, so they will not be retrieved from the database in that case. There is another variation of this algorithm, which is DBN25, which helps you to decide how you want, how the impact of the term frequency and also the document length. You can tune it that by the parameter K and B. So, for example, in the TF-IDF that we saw before, if the word Drupal is 10 times in the document, it score X, but if it's 20 times, it will score 2 times X. While with BN25, it will score X if it's 10 times, but then we do like 1.3 times the previous score if it's mentioned 20 times. So we normalize that so it has a little bit more weight. The same thing happened with the document length normalization. Because in the TF-IDF, the long document are really heavy, they have a heavy penalty, are really heavy penalized. While with the BN25, we can decide that, and we can give a smaller penalty in this way. So we have the K parameter we are passing to the BN25, which is the time frequency. So how much the frequency influences the score, and we can go from 1.2 to 2. And then here we have the length of normalization, degree of normalization for the document length, and it goes from 0 to 1. In this case, you can have a different result, and you can decide how you want to treat the longer document or how you want to treat the term frequency. So now that we know how to do the search, how the BN25 works, which, by the way, most likely already used because it is used in Solr search or in Elasticsearch. So if you are using one of those, you already using the BN25. So in this case, to make a Drupal example, the keyword search becomes Solr search or a Elasticsearch there. The semantic search is the one that we do with the vector database. So we do the search in both databases, and then we combine the results. But to combine the results, you need to use another algorithm, which is the reciprocal rank fusion, which rewards the document for being highly ranked in the list. Basically, assign point based on the position. So the first item will get 1 point, the second item will get 0.5, and so on. And the algorithm is this. For each result, you do 1 divided by k, that we can define is different from the k of BN25, plus the number of the rank is first, second, or third. And we can see in the next slide. So when k is the default 0, so if one document is first, so it will be 1 divided by its first position is 1. But if it's 10, then it's 1 divided by 10, which is the position. And there is too much difference here. So all the top documents will always dominate in this ranking. So what we can do, we can set it to 60, which is typical, and then it becomes like this. So the difference will be just 1/15, which is a little bit more balanced. So then we can set up the beta weighting, so we can decide if we want to give more weight to the semantic search or to the keyword search. So the higher the beta weighting is, the more priority we give to semantic search. For 0.7, for example, is 70% semantic search, 30% keyword. 0.5, 50-50. 0.3 is 30% semantic and 70 keywords. So then it will look like this. So we gave the score to the first document in both, and second, and so on. And then we create this list. So the document B is first because it's in second in the first list, and second in the second list here. So the sum of this score is 322. Then we have the document A, which is fourth here, but first here. So we sum those and the second. And the document C is fifth here and fifth there, so is in both and get higher score. While document D and Y, they are from both, so we get both of them. But we score like this. We sum the scores based on the two lists. So now the issue that the retrieve, so the results are not based only on how we store the content, how we retrieve them. It's also how we write the query. And we know the user can write all type of queries when they are chatting to the chatbot. So in my example here, we use the query parsing. So what we do, for example, the user asks this question. I was setting up a new Drupal site yesterday and ran into this weird issue where the form wasn't validating properly, something about the CSRF token, I think. So as you saw, that's really verbose. There is lots of noise, lots of unwanted information that we don't need. So what we can do, we are going to clean up. So we're going to ask the LLM to rewrite the query. So we are going to pass the query that we have, and we're going to say to the LLM, the user submitted this query to search Drupal documentation. Rewrite it to optimize it for search. So remove unnecessary context, use technical terminology, extract the content intent, and keep it concise. And our example from this becomes this one. So Drupal form validation CSRF token error. And this has a huge impact on the way that, on the result that we're going to get. Because I'm going to pass only the information that we want in a way that the LLM will properly understand it. Then we have other rewrites. So for example, we have an NER, so named entity recognition, where basically we can use this for metadata filtering, for example. If you want to get the document version of the API, or if you want like some specific hook, if the user is looking for some specific hook, we can use that, or for e-commerce with product code, and so on. So this is really useful. And then there is another one, which I never use, is the hypothetical document embeddings. Basically what it does is getting the query from the user, and is generating an answer, an hypothetical answer, embedding those answers, and then searching in the database with those vectors. So I never use it because usually I use or the entity recognition or the query parsing. Then we also have the context ingestion when we do a query to the system. So we can add the user information, we can add the role, the permission, the user ID, all the information that you want. You can add those. So location, and this will have also a massive improvement on the query that you perform. Now that we saw how we can query and how we can store and query, we need to talk about the quality metrics. So the quality metrics is really simple. So we need to have the prompt. So we have a list of prompts that we have. So we're going to do here the evaluation. So the ranked results, and then the test data. So all documents that are labeled relevant. So we are here now in the testing side of the application. So, and I'm going to measure the precision, which is basically counts how many of the returned documents are relevant. And then the recall, how many of the relevant documents that we have in our system are actually returned in the results. So we have precision, which is relevant retrieved document divided by document retrieved, while the recall is relevant retrieved divided by total relevant that we have in our system. So let's say we perform 2 queries. So we have those tests where we have 10 relevant documents in our system. We perform 2 different queries. So in the first query, we have 12 documents returned, but only 8 are relevant. That means that the precision is 66% because it's 8 returned out of the 12 total returned, while the recall are 8 out of 10. So 8 documents are returned out of the 10 that should be actually returned. So the recall is 80%. And then in the second query, we have 15 documents returned, but only 9 are relevant. So the precision went a little bit down, but the recall went a little bit up. So you can use those numbers to test your system and make sure you improve your the way that is doing the query and the results. Then we can talk a little bit about agentic RAG, because everything that we have done previously, we can do it through an agent. So with the basic RAG, we have the fixed retrieval rules. We have one LLM, usually that processes everything. There is no self-correction or interaction. While with agentic RAG, I know they can plan, they can use tools and so on. So they can choose the retrieval strategy. They can use different LLM per task. For example, if you want to do a query rewrite, you can use another LLM, and then to do the embeddings, another one. So you have like more freedom. And then you can do everything at the same time as well if you want. So it will look like this. So here is the agent that is going to perform the search. So it will perform the search, and then we'll do the evaluation, for example. It will check if the results are good, and then it will see if any here of the tools that he has will be useful. Do I need to check other resources? So you can do another check. Should I use the keyword search? So change from semantic to keyword if you want to improve the results. Should I search with a different prompt? So it will rewrite the prompt. Or is this source reliable? So it will do the hallucination check. You can do the ranking. So you can add all the tools and all the instruction here that you want. So final tips and thought. So when you build a RAG system, the infrastructure is really important because like when you choose the tools, like I don't know, Pinecone, or you want to store it in your hardware, the more traffic you have increases the latency and also cost. If you're going to add more memory, again, it's more computed cost, and when you scale, you need to be able to keep the performance high while you are scaling. Then the real data are really messy, even if we know that we structured our site really well, but the content itself is really not really useful, not really well structured sometimes. And then most of the time, the text is not all in text, but you can find also PDF images or slide, for example. And then at that point, you need some extraction tools to get the content from images in PDF and take it out and convert into text and then embedding. There are other tools like Clip and stuff like that that can do multimodal. Then, again, we need to think about the unpredictable prompts from the user. And we need to add some guardrails, something that will tell the LLM to stay within the internal knowledge. And then the last one, and I think is the most important when we build RAG, especially a RAG system, because when we build a RAG system and we store a different database, we are outside of Drupal. So the security and privacy is really important. You need to be able to check if the user has real access even to the single chunk, not to the entire document, even to the chunk, because even just one mistake can bring to a data leak. And again, because there is no default permission check, you need to check. You need to be careful on that. And you can use the metadata for that. You can add the role, the user ID, or whatever, and then you can also use Drupal. So retrieve the chunk, see which content belongs to, and see if it has access. But it's a longer process. So in the metadata will be much simpler. Okay, and so quick recap. Before the recap, I want to give a special mention to all the topics that didn't make it through the slides, because RAG system is really huge. So we have quantization, which improves the velocity, because quantization is basically the compression of the LLM. I couldn't talk about specific tools like monitoring and logging, or LangChain, OpenRAG, OpenSearch, and then workflow. This would be really nice. GraphRAG, that creates relationship between the embeddings. So for example, between the chunks, for example, if you have a phrase like Vincenzo is a Drupal speaker, it can become, for example, the Drupal speaker are in this list, and then you can find my name there. So it's creating those kind of relationship. Multimodal is the one that I was talking about with images, PDF, and a slide, for example. That's really important, but I needed just another hour to talk about all those, and then the cost control. So hopefully you like it, because today we talk about RAG and CAG, chunking and metadata. The hybrid search, we saw this sparse versus dense vector. We saw how we can refine, evaluating, and the metrics. So hopefully you liked this presentation, and thank you. Any questions? and so forth.
Hello, can you hear me?
Yeah.
I can directly ask.
Okay.
So you specified 3 search strategies, keyword, semantic, and hybrid.
Okay.
So most of the time when user is doing a search, they want the search to understand what they are asking and give the answers. So semantic seems like most of the time what user wants.
Okay.
So why would you go for a hybrid search over a semantic search? I mean, and what could be the cases where you just go with semantic or just go with
Okay. So you can.
hybrid search?
So you can do a hybrid search when you want like more results, to have different results from different sources, for example, and you want to combine them into one, or you want like more reliable like results. So you go from both of them, and then you get the one that are really important from both.